We saw that electromagnetic waves consist of oscillating electric and magnetic fields that are perpendicular to each other, and that electromagnetic waves are transverse waves because the oscillations of the electric and magnetic fields are perpendicular to the direction that the wave propagates, where the speed of an EM wave is the speed of light. And note that electromagnetic waves are spherical, so they propagate outwards from the source, but at some distance away, they become flatter and flatter. So that's why they're commonly assumed to be planar waves, as we saw in geometric optics. And unlike mechanical waves, like sound waves, electromagnetic waves don't need a medium to propagate. So electromagnetic waves can be produced by oscillating charges. So recall our inductor capacitor circuit, which resulted in the oscillation of the current. So a charge like an electron, for example, can oscillate up and down, and this oscillation will produce an electromagnetic wave. So similar to how we held a string at one end and moved it up and down, and that resulted in a wave propagating through the string. So it's a similar concept here. And the frequency of the oscillation being equal to the reciprocal of the square root of the inductance by the capacitance. So an example is if the inductor had an inductance of 1 microhenry, or 10 to the minus 6 henries, and the capacitance of the capacitor is 1 microfarad, or 10 to the minus 6 farads. So that would give an angular frequency which would divide by 2 pi to get the frequency of the oscillation in hertz. So in this case, the frequency would be around 160 kilohertz or 160,000 hertz. And when we look at the electromagnetic spectrum, we'll see that a wave with this frequency is characterized as a microwave, which are used for long-range communications, such as between mobile phones. And recall that we can calculate the wavelength, being the distance between 2 peaks or 2 troughs, and so on, of a wave, which is equal to the wave speed of the electromagnetic wave. So in air, that's almost equal to the speed of light in a vacuum. And we divide this by the frequency in hertz, which is in 1 seconds, and the seconds cancel, and we get a wavelength of around 1.9 kilometers. So the higher the frequency, the smaller the wavelength. The electromagnetic spectrum groups electromagnetic waves into categories that are characterized by their wavelengths. So these categories include radio waves, which are used for long-range communication, such as in the case of a mobile phone. And this is followed by microwaves. So for example, the waves in a microwave to heat up food. And an example of an infrared wave is the heat or energy emitted by a thermal body. So infrared means it's below red. And then we have visible light. So the wavelengths are characterized from red to violet. And we'll go into that in a bit more detail. And then we have UV or ultraviolet rays, being above violet. And an example is sunlight. And then you have X-rays used in medical imaging, and followed by gamma rays. So these are the most damaging. And an example is a supernova explosion. So on the left hand side, we have the frequency, and as we move up the spectrum, the frequency increases. So the energy of the wave increases with frequency. And as the frequency increases, the wavelength decreases as we move up the spectrum. So remember that the EM wave consists of electric fields and magnetic fields oscillating perpendicular to each other and perpendicular to the direction of motion of the wave. And the wavelength is the distance between successive peaks or troughs and so on. So the higher the frequency, the smaller the wavelength. And therefore the wavelength increases as we move down the electromagnetic spectrum. Now visible electromagnetic waves in this part of the spectrum are broken down into color categories, and in order of decreasing wavelength as we move up the EM spectrum. So we have the red category having a higher wavelength than the orange category, and that's followed by yellow, green, blue and violet. And visible electromagnetic waves are also called light waves. And electromagnetic waves of all wavelengths are also referred to as light or electromagnetic radiation. So here is an example of a mobile phone. So the microphone records your voice, which is made up of sound waves propagating through air. So this sound wave is converted into an EM wave signal through the oscillation of charge on the antenna. And then when this charge oscillates, it produces an electromagnetic wave that propagates in all directions. So remember that EM waves are spherical, and then the wave reaches an antenna attached to the mobile phone tower, which transmits the signal to the other phone. So that's the basic idea of an application. So what's important is remembering the ordering of these categories in the EM spectrum and the ordering of the colors of visible light. So you can start from red, which is above infrared, and go to violet, which is below the ultraviolet category. And the other colors are more or less intuitive. So orange and yellow are close to red. So you have Roy. And then you have green and blue being closer to violet. Given that an EM wave has an oscillating electric field and perpendicular magnetic field, so being a transverse wave, these oscillate perpendicular to the direction that the wave propagates at the speed of light, then we can idealize it as an LC circuit where part of the energy is stored in the electric field of the capacitor and part of the energy in the magnetic field of the inductor. So recall when the switch is closed, the current in the circuit oscillates back and forth through this circuit. So the energy stored in the capacitor is equal to 1/2 by the capacitance by the square of the voltage, and the energy stored in the inductor is 1/2 by the inductance by the square of the current. And recall for a parallel plate capacitor, the capacitance is the dielectric constant by the electric permittivity of free space by the area of one plate of the capacitor over the distance between the plates. And the voltage is equal to the magnitude of the electric field by the distance between the plates. And squaring this gives the following result. And then multiplying this by 1/2 we have the energy stored in the electric field of the capacitor. So if we cancel out one of the D's and take the case where there's no dielectric between the parallel plates of the capacitor, as an EM wave propagates through air, which is basically treated as free space, then the dielectric constant is taken as 1. And now if we divide through by the volume occupied by the electric field, which is the cross-sectional area of the capacitor plate, by the distance between the plates, then we get the energy density of the electric field, which is 1/2 by epsilon naught by E squared. And recalling the inductance of a solenoid is the magnetic permeability of the core, and we'll assume the core has nothing in it, so we take the magnetic permeability of free space by the number of turns of the solenoid by the cross-sectional area of the solenoid on the length. And the magnetic field in the solenoid is related to the current by the magnetic permeability and a number of turns per unit length. So therefore we can write the current squared as B squared on mu naught squared by N squared. And then multiply by 1/2 gives the energy stored in the magnetic field of the inductor. And a number of turns is equal to the number of turns per unit length by the length of the solenoid. So that would be N squared L squared. And now we can cancel N squared and one of the L's and one of the mu naughts. And the cross-sectional area of the solenoid by the length is the volume occupied by the magnetic field. So dividing through by AL, we get the energy density of the magnetic field, which is 1/2 mu naught by B squared. Now recall that a charge moving in a magnetic field at a speed v induces an electric field equal to V times B. And in our case of an electromagnetic wave, the speed of the wave is equal to the speed of light. So therefore we can write B squared as E squared on C squared. And now using the relationship between the speed of light and the electric permittivity by the magnetic permeability, we have mu naught by C squared is 1/epsilon naught. So therefore, this becomes epsilon naught in a numerator. And therefore the energy density of the magnetic field is 1/2 epsilon naught by E squared. And therefore the energy density of the electromagnetic wave is the sum of the energy density of the electric field and the energy density of the magnetic field. So that will be epsilon naught by E squared. So therefore the energy density of an electromagnetic wave is proportional to the square of the strength of the electric field. And half the energy is stored in the electric field and half in the magnetic field.